Hi, good morning, and welcome to the ZP Developer Zone. So we do this webinar every Thursday at 8 a.m. London time, and we do it really to answer kind of questions that have come in during the week. So I'm just checking that we've actually got connection at the moment, so I hope we have, because I'm essentially doing this from a hotel, right? So let me jump into it. All right, so the reason I'm doing it from a hotel is because you'll see in a minute that we do these workshops, and we happen to be doing a workshop today. But don't forget the ZP Academy. There are a couple of free courses on the ZP Academy. It's probably worth saying that if you're one of the questions that's this week is what's the sort of modality of your sensors, whether it's a glucose sensor, a lactate sensor, an oxygen sensor, a pH sensor, what's the modality of your sensor? And that's probably pretty well covered in the in the ZP Academy. That of those sensors I just mentioned, the enzyme sensors and the oxygen sensor, for example, are amperometric. The pH sensor is an ion selective electrode. If you're doing conductivity, then that would be a form of impedance measurement, but there are sort of electrochemical techniques in general. We do these webinars, so every Thursday at 8 a.m. London time, we do a webinar and we try to answer technical questions there. We do collaborations. Collaborations are strictly speaking, I would say, really with academia, and it has to sort of be a win-win situation. We do offer jobs. I'm really glad to say that I'm really sorry about the kind of global economy, but we are riding through this okay. We have our ZP Developer Zone, and we have our workshops. So, like I say, it was a bit of a shaky start because I'm actually doing this from a hotel today because we have a workshop going on this morning. Let me jump a little bit quicker. Don't forget the workshops, of course. I should remind myself that every time you see a link, I will have posted the link underneath the video. So if you want to come to one of our workshops, then this link will show you what's going on in 2023. And it's probably worth saying that some of our workshops can quite heavily feature CGM, cortisol, things like that. So if you're kind of curious about these things, don't hesitate to come to our workshops. It's probably worth saying that CGM, or continuous glucose monitoring, that workshop's as relevant for somebody who's trying to make sensors for diabetics, and it's just as relevant for somebody who's trying to make sensing in bioreactors and cell culture as well. So the questions that came in to do today was somebody's very interested in putting our electrodes, or sensors, I should say, into cell culture and bioreactors. I've actually got a couple of questions around this, so this seems to be quite interesting at the moment. Somebody else wanted to know screen printed electrodes for protein detection, which I will discuss today. Somebody else, it was really on the YouTube channel, wanted to know about Faradaic and why their Faradaic impedance was drifting. Somebody else wanted to know some more specs about our ammonium sensor, so I'll cover that. Another questioner came in and sort of from one of the universities at Imperial, wanted to know, what kind of applications are we interested in? I think the applications we're interested in are a lot of applications. I think the only ones that we're not interested necessarily are defense. We tend to sort of have a motto, which is, do good. And so, we try to, or we do things that kind of link to health and well-being, things that are linked to sort of water quality and sanitation, things that are linked to sort of food production, things that are linked to kind of environmental improvement, but not so much industries or applications, that are in the defense realm. It doesn't sort of fit in with our ethos at ZP. I have some questions about CGM, continuous glucose monitoring. I will answer those. Also, a question about how do I access this cortisol sensor. So it's not a great answer from me, but I will touch upon it. Where to find the chloride resilient pH sensors. I'll touch on that. Sensors for bioprocessing. So I realized that question 1 and question 9 are quite related, actually. And then question 10 was about nitrate sensing. So in terms of cell culture, obviously we have our glucose sensor, our conductivity sensor. We also have some electronics called single-purpose biosensor circuits. So those single-purpose biosensor circuits we sort of configure them. You know, if you've got a glucose sensor, then you'll need the glucose version. If you have a conductivity sensor, you need the conductivity version, etc. Whenever we sell these kind of sensors these days, we do recommend that people get some engineering support because, you know, ZP now, you know, this is like our 8th year of being in operation. Of course, you learn a lot over the years, and you realize that, you know, it's not enough just to give people sensors. You do actually have to provide service around them as well, because sensors are an unusual, at least biosensors are an unusual category of sensors, because the sensors are in very intimate contact with the sample. So it's not like a temperature sensor or a pressure sensor where there's often some material between the sensing element and the sample. No, these sensors are really in contact with the sample, so it's a lot more subtle, let's say. And you know, the fact that, you know, some of us have been in this industry 22 years, at least the company's been around 8 years, then, you know, there's a lot of experience that needs to be brought into how to apply these sensors. I say here, question number 1. Let me have a quick look. Yeah, I say question 2 here, but that's wrong. So they're interested in our glucose sensor and our lactate sensor and oxygen sensor conductivity. And the question is, are these sensors continuous? It should be said that you know, that we try to make all of our sensors continuous. So the glucose sensor is continuous. Later on in this presentation, I'll show you that one of these glucose sensors has been running 125 days minimum. It's probably been closer to a year at this point. So they are designed to be continuous. The oxygen sensor is designed to be continuous. The conductivity is continuous. The pH sensor is continuous. The lactate sensor is it's the most feeble of the biosensors. So it is designed to be continuous, but the enzyme can be overwhelmed. So we've kind of got 8 hours run out of that. So that's why I'm kind of tending towards people to look at the glucose and the oxygen, the pH, the conductivity. With the lactate sensor, if we want longer runtime on it, we have to adjust some of the polymers. So that's the sort of one of the subtleties of why it's not enough to just buy the product. Unfortunately, there needs to be some support. I have put a link here that we have already started with some universities, sort of putting our sensors into their bioreactors. So I've kind of listed some useful or a useful link there, and hopefully I did put that link underneath the video as well. Let me just the reason that when putting sensors into bioreactors, we have to treat it as a bit of a service, because actually when you think about it, the bioreactors are in so many configurations. So the configuration is a variable, the cells could be a variable, the length of that bioreactor, that cell culture is going to run for is a variable. The let's say the solution itself, or the is also a variable. So there's so many variables in this that you can't just have a sort of one fit or one product fits all scenario. And we do have a lot of hardware and a lot of sensors around this, and a cloud database, so the data can actually go to the cloud. But really, if people are if there's not enough information on the website, then I think it does come down to, so as I say here, products as a service, that we do have to kind of come in on a project and, you know, discuss what you're trying to do and getting into a lot more detail on that. But it does require budget for us to get involved. So here's some useful links: the glucose sensor, the pH sensor, the oxygen sensor, and the conductivity sensor. I realized I didn't put a link to the single-purpose circuit, but we do have a data sheet on that as well. And as I say, here's also a link to our engineering services as well. Another question that came in this week was about protein detection. Somebody wants to detect proteins on a carbon electrode. I do put a link to this. This is our hypervalue carbon electrode. It can be functionalized with something that's called pyrene NHS. The pyrene is very good at essentially it pi bonds, I would say, to the surface of the carbon of our electrode, and the NHS is a very sort of active moiety that allows you then to bind antibodies to it, and you can block that surface with chitosan or BSA, bovine serum albumin. And as you do that kind of modification so that you can detect either proteins or antibodies or something like that, we often follow that sort of modification process using cyclic voltammetry. It's probably worth saying that we do go into this in quite a lot of detail actually in these workshops that we do, but we do develop sensors for the detection of protein. Protein is a sort of very broad term, so protein could mean enzymes, it can obviously mean antibodies, so I'm sort of, or antigens, I should say as well. But we build sensors which are sort of immunotype sensors. When the target binds, the surface changes, and we can measure that change using something like differential pulse voltammetry, which reminds me, I think we've done quite a nice video on differential pulse voltammetry on the YouTube channel as well. So if you're not familiar with DPV, differential pulse voltammetry, there is quite a nice video about that covers cyclic voltammetry, differential pulse voltammetry, square wave voltammetry as well. So I think carbon electrodes are a good platform upon which to make sensors for proteins, and we do it quite a lot. And the electrode we suggest is not obviously, but the biggest user of this hypervalue electrode is actually us at ZP, so we really know the quality on this electrode. Again, that link should be underneath. I just want to say this is a really hard question for me, that somebody's interested in Faradaic impedance and the drift in Faradaic impedance. The question, why something is drifting, it was a YouTube conversation. So why something is drifting is, something's changing. So is the underlying electrode changing? So, an electrode could be corroding, that would give you drift. Do you have polymers on top of the electrode or layers on top of the electrode? Those layers are probably kind of, soft materials, so they could definitely change. So that would give you a drift. Or your solution is changing in some way. So why something is drifting is, it could be the electrode, it could be the way you've modified the electrode, or it could be the solution itself. My guess is the solution is fairly stable, as long as it's probably fairly stable. I don't know, is there something precipitating? Is there pH change? So solution is probably okay. If you've modified those electrodes, that will be a definite indication, or that's a definite source of drift. And then the underlying electrodes, things like carbon are quite inert. Gold and platinum are actually a bit more active than sort of some people sometimes realize. So the answer is, without detail, I can't really know what the source of drift is. But, like I said, I can list out at least 3 sources of drift in your Faradaic impedance experiments. We do cover Faradaic impedance in the workshops as well. It's worth saying that we are going to do another online workshop. So there are some links, but I'm not sure that I've linked the online workshop, but I am organizing an online workshop as well. Question number 4 was about specifications for ammonium sensors. Again, here's a link. I'll just move myself out of the way of the image. But when I say there's a link here, it's also underneath the video as well, because there's a page here. There's a data sheet here. There's some representative data here, and there's a good video here of us actually using that sensor. So this is what we have in the public domain, and essentially this is what we've got. So if you need more, then I think you'd have to come to a workshop and dig in a little bit deeper with us. This is a question really about applications. I sort of stated it already, but at ZP, we're quite broad in our interests. This is our food sense, for use for measuring the hotness of chili. I know the questioner knows this. This is a sensor that we developed with PWB for measuring nitrate in the soil. This is a sensor, interestingly, this is a sensor that measures glucose and cortisol in fish. And this is the same, we call it fish tag sensor in fruit, trying to sort of measure the sugars in fruit. And this is a big part of what we do, which is wearable sensors, measuring sort of lactate in sweat. And we do a lot of sort of spot testing, testing a drop of blood, testing some tear film, testing some saliva. So here I can look at food production. I can see agriculture in here. I can see aquaculture in here. I can see well-being in here, and I can see health in here. But what is not in here, and I said it already, is things that are sort of overtly linked to the defense industry. I think it's it's an important industry, but it's just not something that we're involved in, or I think seek to get involved in. Question number 6. I suppose it's worth saying at this point that we're aligned with the UN sustainability goals. So a lot of what we try to do is, there's this headline sort of slogan, do good. Yeah, we want to do good, and therefore we're aligned ourselves with the UN sustainability goals. So we try to make our business and our technology align with really improving sustainability and sort of outcomes for people in general. And a CGM, somebody's got one of our glucose sensors. They have some very specific questions around it, so I need to sort of jump in. Hard to answer all these questions, but so they want to know about, they're using our generation 2 glucose and generation 2 lactate sensors. They say here, see that your bias voltage, I've suggested to them, is 0 millivolts. It's not, that 0 millivolts is not an absolute voltage. It's a relative voltage to the reference electrode. But absolute 0 in this world is probably what we call ground. It's just saying that you're applying a voltage versus the reference voltage of 0 millivolts. It doesn't mean actually there is no voltage. I know it sounds a bit of a sort of so it sounds unusual, but and it is quite hard, but to get your head around. But let's say there's an absolute voltage in this world, and there's a reference voltage. We're telling you to apply 0 voltage versus this reference, but it's not the world's absolute 0 voltage. It's just relative to a reference. So you are actually still applying energy. It's just that energy versus the internal reference seems to be 0, but it's not. It's actually but actually that reference voltage that reference that you're applying the voltage versus is just a local reference. It's not the global voltage reference. So you are applying a potential. It's just versus the reference, it says 0, but versus absolute 0 voltage, it's not 0. When we tell you to apply 650 millivolts, we're often telling you to apply 650 millivolts because a lot of sensors in, let's say, biosensors are a class of enzymes called oxidases. Now, I do cover this in workshops. And oxidases often react with the analyte and oxygen, and they produce hydrogen peroxide. And hydrogen peroxide is easily detected at 650 millivolts. So that's where the 650 millivolts comes from. There's not a formulation. There's not a formula for this. I talk about it in the workshops, but actually you should really use voltammetry to determine where the best voltage is. Does the bias voltage depend on the generation of the sensor? Yes, because if you detect hydrogen peroxide directly, then you need 650 millivolts. If you detect hydrogen peroxide indirectly via a catalytic surface, then you need less voltage. Do things like electrode design or electrode design and geometry influence the bias voltage? They do. This is really, you're really going down the rabbit hole here. You can actually run biosensors in 3 electrode mode or TO electrode mode. So that's a change in electrode, let's say, design, going from 3 electrodes to 2 electrodes. That will influence your bias voltage. If you went to 2 electrode mode and you had the electrodes this far apart, or this far apart, or this far apart, that would influence the bias voltage. So the answer is yes, it is actually quite complicated, but it's actually voltammetry that would actually allow you, again, you would do a voltammetry on your system. You would see where your oxidation or reduction peaks were, and then you would set your bias voltage where the voltammetry was indicating your electrochemical activity was. It's probably worth saying. I mean, that is quite a conversation, and I'd probably spend about 45 minutes explaining that in one of our workshops. Does the bias voltage depend on the recognition element? Yes, it does. So, if it was an oxidase enzyme, that would be 1 voltage. If it was a dehydrogenase enzyme, that would be a different enzyme cascade, and you'd end up using a different voltage. This is an interesting one here. He stores some sensors in the fridge, and he stores some sensors at room temperature. I suppose what this is telling you is that it's probably the enzyme is degrading. I'm a bit surprised with the glucose sensor. It's really robust, but if the enzyme is degrading, then maybe you're telling yourself here that the fridge gives you longer lifetime. So that's how I'd interpret that. Just out of interest, we call it a generation 2 sensor sometimes. I should really call it a generation 1.5 sensor. This is what we've been essentially shipping to you, either in glucose form or in lactate form. Again, I think the workshops are probably the best place to do this. These slides are from there, but we take the electrode, we put a catalytic layer on it, we put an enzyme layer on it, we put what's called a barrier layer on it. Let's see, there's a lot going on there. The glucose, some of it gets to the enzyme, it reacts in the presence of glucose oxidase, and in the presence of oxygen, and we get hydrogen peroxide. Now that hydrogen peroxide is not directly detected. We actually have a catalyst in there that's helping to take electrons from hydrogen peroxide and helps to take them to the electrode surface. And therefore, that's where that 0 millivolts comes from, because catalysts, by definition, they don't change the course of a reaction. They just change the energy by which that reaction takes place. So rather than applying a bias voltage at 650 millivolts, you can now get away with 0 millivolts. So that's kind of why we're recommending 0 rather than 650. Just a small introduction to voltammetry. The question is, which potential, or maybe I should say which bias should I apply? Run a cyclovvoltammogram, spot where your peaks appear. So this is a animation of a cyclovvoltammogram. And in this case, we would run this cyclovvoltammogram and we would say, okay, there's a peak here, it's quite big. It seems to be centered around about, this is not for hydrogen peroxide, by the way, but that's centered, it just happens to be centered around about 600 millivolts, and that would be a good place to, for example, for us to apply the potential or the bias voltage when using it as a sensor. Yeah, so these are those questions again, I think, and I think I have actually answered them. Question number 7. This is a hard one to answer because we do have a cortisol sensor. I think I mentioned earlier on that there were some pictures of a fish and an implantable module. So we are actually putting cortisol sensors into one of the most. Oh, that's so nice. So we got a nice reply there. Thanks very much on that. So why do we need any bias relative to reference for generation 2 sensors? Because your volt, you are actually applying 0 volts. If you didn't apply anything, you just turned it off, there really is no energy being applied. So you kind of think that 0 volts versus reference is 0 volts. But I suppose when you think about your electronics, there is a ground in there. So you're not sort of necessarily applying 0 volts versus ground. You're actually applying 0 volts versus reference. So so I know I must admit, I am an electrochemist, not an electronics guy. So it's sometimes a little bit, I'm stumbling a little bit, but it's not 0 volts. It's 0 volts versus reference. So you do have to put some voltage versus reference, or not some, but I mean, it might make it easier if I told you to apply 1 millivolt versus reference, because 1 millivolts is essentially the same as 0 volts. But it's so small. But then you would say, all right, now I am applying something. But the quick answer is if you apply no volts versus, like you say, you didn't essentially apply any power, sensor, in my opinion, would work. I shouldn't say that, because then I always know scenarios where things appear to be working. The cortisol sensor is something that people are very interested in getting hold of. Sorry, the reason I went off on a tangent there, I was just looking at the questions coming through the YouTube streaming. So the cortisol sensor is something that we do have, but unfortunately we only make it available through projects with clients. It's a very valuable sensor, and it's very nuanced. You really need to be involved quite deeply with that client in that. So it's not something that we can just make available to sort of projects that are not funded well enough to actually support that sensor. So the quick answer is we don't just put it on the open market. Unfortunately, you do have to be in a project with us, and it does have to be a very well-funded project. You know, sort of typical project like that would sort of involve a well-funded California startup. I do want to talk about actually measuring analytes on the skin. I mean, this is something that we've done in the past where we took one of our lactate sensors, we put it into a microfluidics device, we put the microfluidics device on the skin. We put that device plus electronics, there's the electronics, there's the patch, onto one of our guys. He was cycling, we were making Bluetooth connection to the laptop. In this case, we were able to follow the lactate as a function of time, and it really is a function of exertion. So he was starting, he was perspiring, he was straining, and that's where we actually got this signal. It's kind of interesting because we looked at the literature as well, and we actually see that essentially the dip that we get here is the same as that we see in the literature as well. So it's kind of a curious phenomenon, and we haven't determined yet if that's a physiological phenomenon or actually maybe a microfluidics phenomenon. Now, the reason I brought that up is because I didn't like to say that, look, you know, that cortisol sensor is not something that we can make available unless it's in a well-funded program with a commercial company. But I did want to show you that, you know, the idea of measuring analytes on the skin is perfectly reasonable, and this lactate data is something that, you know, we have in the public domain. The last one, there's a couple more questions. This one is about measuring pH using what we call a chloride resilient pH sensor. The person was actually struggling to find it, so I have put a link. The link is underneath the video, so follow the link. The item is here, and you'll find the chloride resilient sensor there's a drop down menu here. If you click that, you find it in there, and I'm sorry that it's got hidden away like that. I'm just reading the comments here. If I take a sensor and it is dry, do I need to have it in water PBS for some time? Yeah, I would say that's correct. So, for example, something that was, the question here is that somebody wants to get a glucose sensor to kind of give them a reasonable signal in a short amount of time. Glucose sensors are often made in what we call a dehydrated state. So the first time they see water, they basically soak up that water and they kind of reconfigure the polymers. So you find that sensors actually, especially glucose sensors, get better with time. And so it's not a bad idea to sort of, you know, if you run a glucose sensor, the second time you run it, you'll find that the break-in time is a lot, or the equilibrium time is a lot faster. So the quick answer is yes, and it's because once it's seen water, it's kind of hydrated. So even if you dry it, it doesn't come back to its original manufacturing configuration. It actually comes back to a more hydrated configuration. So that is a trick that you should pull. Yeah, it says here, so in the first 500 seconds, the detection of a analyte is not reliable. This is really something that we have to cover in the workshops, but in the first 500 seconds, we let it equilibrate. If we were trying to do what's called a SMBG, a self-monitoring blood glucose reading, where we were actually making a sensor to detect glucose in a drop of blood, that has to happen in 5 seconds. So the 500 seconds that you're seeing is because that sensor has been configured for continuous glucose monitoring. If we were actually trying to have a different application, trying to measure just a drop of blood, then we would actually use a different configuration of sensor. Question number 9 is about sensors in medical and bioprocessing. Are your sensors multiplexable? Yes, they are. We can actually use, essentially these are electrochemical sensors. So people with R&D potentiostats can run our sensors. Obviously, I prefer to use our potentiostat. It's easier to support, but the quick answer is, yeah, you can use like lab instruments to run our sensors. If you're trying to measure the oxygen sensor, then it's an amperometric measurement. If you're trying to measure the pH sensor, it's an OCP, open circuit potential measurement. Conductivity, we would be using an impedance type measurement. It's something, actually, I'm glad I brought this back up, actually, because I was disappointed with my response on the cortisol, but it's probably worth saying that we have been developing these little capsules. This is the electronics to drive these capsules. And we've been testing with things like glucose to make sure that they work. So what we've been up to really is we've been making these little tiny electronics, because actually we've been making sensors that are either wearable or implantable. And these electronics will drive any of our sensors. So if people want to put essentially sensors into cell culture or sensors into bioreactors, etc., we do have the electronics for that. Our sensors, this is back to, it almost reverts back to question number one here. Yeah, our sensors are continuous, especially those glucose sensors. They're really continuous and have quite good lifetime. This is probably a generation 1 glucose sensor, but it's been running for over 125 days. I love glucose oxidase. It's really robust. Electronics wise, there's an, if we were doing R&D, we would use this potentiostat. We actually have, and I'm going to link into it here, for example, 6-channel instruments that we can measure, 6 biosensors in parallel. And then I also bring in this tiny little set of electronics, because it sort of demonstrates that the package doesn't have to be super big in order to drive that. So I've got a few links that could be useful there. When people have, this is a slightly side note, but when people have intellectual property, rather than just jumping straight into it, what we tried to do at Zimmer Peacock is we tried to do sort of a technology market fit. So there is a lot of IP and papers written in this world, and you can read them. But I actually recommend that at ZP we do a technology market fit, which kind of says, right, let's look at the technology and let's brainstorm about where this technology can be used for. So we do this as a service. I recently did it for a UK university where they had an application in mind, and they had some intellectual property in mind. But we said, this application that you're trying to exploit, it's not very definable. It's actually an application in its nascence, in its birth. And so we actually had to kind of advise them to not pursue the original application, but actually to pursue some other applications. So this is something that we do with academics. Is we get we essentially get sort of brought in as consultants, and we will actually look at the technology, because we're pretty good at understanding the technology, but we're also good at understanding markets, and we'll actually do what we call a technology market fit and make sure that this technology is going in the right direction. Because if the market, if the sort of application's all wrong for the technology, then you're just going to build effort upon effort, but the foundations of the whole thing are commercially not sound. I just want to touch on nitrate sensors. So we did some work with PBS and JIC in the UK, where we, you can see here, we took one of our hypervalue electrodes and we ended up embedding them so we could put them underwater, and we ended up putting them into what's called a rod, and I'll explain that. So here's the sensor, this is the rod, and actually this rod gets sunk into the soil, and we're measuring nitrate at 30 centimeters and 60 centimeters, for example. A lot of our sensors happen to fall into this category of ISEs, ion selective electrodes. This is a nitrate data that we just gathered in the lab. But obviously we've actually been quite good, and we've taken these sensors out to the field. You can see them sort of embedded in the soil there. And actually, we've taken them to farms, and we've measured this is the nitrates here. We've got sort of several sensors here. We've been measuring the nitrate during the growing season, seeing how it jumps up, how it creeps up, how it falls back down again, and essentially how it jumps back up again. So we've had these sensors, the whole timeline here is about 18th of March till about the 16th of June. So it was approximately, I think, March, April, May, June. It's about 3 months worth of continuous operation there. And we've had sensors with PWB and JIC in the ground for a lot longer. So we do have some good experience at Zimmer and Peacock on measuring nutrients in the soil. So when it comes to cell culture monitoring bioreactor, I think it's probably worth, the first stage is not necessarily jumping into the sensors themselves, but jumping into a paid program with us. Screen printed electrodes for protein detection. I think those hypervalued carbon electrodes are good. The Faradaic impedance, as I say, I have listed out 3 places where the drift may be coming from. Ammonium sensors, there's definitely a data sheet, data on that website, and a video about us testing it, so I hope that's enough. Applications to ZP, we're really interested in applications from health, sports, and industrial. We just tend not to do defense. CDM, continuous glucose monitoring. I do appreciate you coming online this morning and having a bit of a chat. So we were, sometimes if I'm jumping around a bit, it's because we do try to answer questions live in the chat. So thank you very much. The cortisol sensor, I'm sorry about that. We generally use this sensor with well-funded companies. But I hope just having a look at that lactate data was kind of interest to you as well. The chloride resilient pH sensor, hopefully you'll find that link and you'll find that the sensor is still on the website. Sensors for bioprocessing, this is linked to, in some ways linked to question 1. Except I would say when people send me IP, I had a look at the IP and it's probably worth doing a technology market fit to make sure that the application and the IP, let's say, fit each other well enough. And then the nitrate sensor, I just thought, I'll show you that we've actually done quite a bit around nitrate sensing, and it's something we're kind of interested in. Okay, so I want to say thank you very much. I apologize, it's quite long this morning. I started this webinar quite early. I have to sort of basically run to do a workshop now, but if you have any questions, as you can see, we try to make sure that we sort of answer these questions as they come in. Otherwise, I wish you a good day. Thanks very much.